So, I have written a script here that will performs the iterative algorithm that I just outlined. The script here, the script is shown here, and you should be able to get the script from the web. When we post the lecture notes, we will also post the script. So, let me run the script and show you how the iterative algorithm works. So, what I am doing here is I am actually using Wavelab to get the low pass filter coefficients. I can use the wavelet toolbox as well, does not matter. And what I am interested in here is generating the Dobeschi wavelet of vanishing moments 2. In fact, if you look at the line here, it says that it is asking for the filter coefficients corresponding to Dobeschi family with a number 4 here. This number is not the vanishing moments, but the length of the filter. That is why I said there are conventions where people use the length as the specification, or half the length, which is a vanishing moments, as a specification. Here in Wavelab, the make on filter, on means orthonormal, that routine requires you to specify the length rather than the vanishing moments. So, I am asking for the filter coefficients here, and I am interested in generating the phi of t corresponding to this dB2, and the accuracy of your phi of t depends on how many times you run through that algorithm that we just discussed. How do we initialize our phi of t? Well, one thing I know for sure, that phi of t cannot have a 0 average, because it is a low pass filter. So, what I am going to do is I am going to initialize my phi of t as a bunch of 1s, just a vector of 1s, right. In fact, ideally I should be initializing such that it is not 1s, but 1 over n, 1 over 4, so that the sum of it, in fact the area under that of phi of t should come out to be 1 and so on, but we will not do that. That normalization we will do later on. So, as you can see here, my initial guess is that phi of t is taking on a value of 1 over a certain interval, right. So, this is how the initial one looks like. Let me show you the initial Dobeschi wavelet, initial guess of the Dobeschi wavelet is just a plain straight line, that is it. Obviously, I know this is not dB2, but the iterative algorithm magically constructs the dB2. Let us quickly see how it looks like in when I run through the iterations. I will take you, let me run this here and then I will take you through the animation. So, suppose I run it for about 9 iterations. What I have with me here are the Dobeschi scaling function. Look at how it magically constructed the Dobeschi wavelet from a guess, but that guess is very important. You have to give a guess that makes sense. You can't give a guess such that it has a 0 average. That's all. So, as long as you give a phi of t that has non-zero average, it should work fine. And of course, here what you see on the x axis, it says time, but it is not time really, it is a number of points over which I have computed iteratively. I started off with 4 points, but with every iteration it is doubled. The number of points is doubled. The time interval over which it exists is actually 0 to 3. Why? Because dB2 has 4 filter coefficients, therefore, its support is over n1 comma n2, 0, n1 is 0, n2 is 3, right. That is, I have 4 filter coefficients at n equals 0, 1, 2, 3. And what are those filter coefficients? Well, those filter coefficients are here. You can also obtain these filter coefficients from MATLAB's wavelet toolbox. There is 4 filter coefficients at n equals 0, 1, 2, 3. So, the support of h is over 0, 3. By the result that we have seen earlier, support of phi is also over 0, 3. So, what you see as a plot here is actually over 0 comma 3. So, the time this is only the number of points from 0 to 3, all right. And the associated wavelet has also been constructed. The moment I have my scaling function, I can also run the same algorithm by starting off with a guess for the wavelet, and this is how the wavelet is built. So, if you look at the code, the way I have written is this is the wavelet function, and all I do is, remember, the wavelet at any stage is a convolution of g with the scaling function, right, because that is from the scaling relation. The psi of t is integral g of t phi of t minus n, h of g of n phi of t minus n, sigma g of n phi of t minus n, that is it. So, I use that convolution expression and compute the wavelet. I do not have to run another iterative algorithm at all. All I need to do is generate phi of t and I will get my phi of t. So, I hope you understand what is being done here. Essentially, this is a scaling relation that we have seen earlier. So, let me also show you, just to make the thing very effective, that is for you to see the gradual guess refinement of phi of t across iterations. I am going to take you to another presentation that I have from a previous workshop, where this is the initial guess, second second guess, this is the development, in fact after 3 iterations, and then gradually it develops 4th iteration, 5th iteration, 6th, 7th, 8th, and that is it. So, then you have the wavelet, right. So, that is called the iterative algorithm for you. Now, as I said earlier, there is also a second algorithm that is known as a cascade algorithm, which has a very beautiful thing to it. It is a very nice way of reconstructing phi of t, it is very elegant. This algorithm works backwards using the reconstruction equation and the following fact. Now, remember that in my MRA, what I am doing is I am constructing approximations of signals that are of finite energy. What I do here is I set the signal as a scaling function itself. Why not? See, even a scaling function is some signal. Now, when I set the signal as a scaling function itself, then I know by the orthonormality property that the inner product between the scaling function and the scaled scaling function is 1. Here I am right now I am looking at scale 1, that is at m equals 0, as you can see from the subscript here, and p here refers to the translate. So, the inner product between the phi of t, which is the scaling function, the continuous one, and the phi of 0 comma p, that is its own translate, in other words. So, it is other way of saying that the inner the phi of t is orthonormal, that is all I am using, that is a property that I am using, but I am rewriting it as an inner product. And I also use the property that the phi and psi are orthonormal at any scale, and here I am choosing 0 scale. But if you look at this result from an approximation coefficient viewpoint, okay, now think carefully. I start from the signal which is phi of t and I start projecting it onto different subspaces V0 or V minus 1 or V minus 2 and so on. Ideally, where does phi of t live? Phi of t lives in the finest scale, right? It lives at V minus infinity. Phi of t lives in V minus infinity, that is when m goes to infinity, that is where phi of t is residing. You can project this phi of t onto any of the subspaces. Let me just show that to you on the graph. So, what is happening here is, as I go here, I get V minus infinity, which is corresponding to m equals infinity. So, when I have phi of t, phi of t resides in this space, really, V of minus infinity, it is actually the finest scale. I can project that, let us say, to V0, which will construct some approximation, because V0, what is it spanned by? V0 is spanned by phi of t minus n and n belonging to the integer set. And what that result says is, whenever I project phi of t onto V naught, there is only going to be one approximation coefficient, that is unity, and all the other approximation coefficients are going to be 0. So, imagine instead of assuming V minus infinity, I have phi of t at a very fine scale. Let us say at very fine scale, maybe m equals 1000. Sorry, m equals, in fact, this is not m equals minus infinity, the m is minus infinity. So, let us say I have over very fine scale m equals minus 1000. What does m equals minus 1000 mean? A very fine scale over a very fine grid, right. So, phi of t is also known over a very fine grid. So, we will just relax that it is continuous, rather imagine that phi of t is now known over an extremely fine grid. When I come from an extremely fine grid to V0, what I would have generated is a bunch of approximation coefficients. It is like taking any signal and I decompose any signal to some level, I have a number of coefficients. That signal is also sampled signal. The number of approximation coefficients, of course, will be much lesser than the original signal, right. So, here also what I am doing is, I am taking phi of t known at some very fine grid, let us say t naught and then t naught plus delta t, phi at t naught 2 delta t and so on. So, very fine grid, and projecting it, here I have a bunch of approximation coefficients. Those approximation coefficients will be of certain length, and what that result says is, when I when I perform a decomposition of phi of t to a level 0, let us say, then what happens? I have a bunch of approximation coefficients which look like 1 and rest of them are all zeros. The length of this, of course, is determined by what length you are looking at, right. In fact, if you have some n grid points here, let me not confuse you with this n here. Let us say I have s grid points here, then by the time I come to 0, the number of coefficients here would be s over 2 power m, 2 power 1000 if that is at 1000, but that does not matter. Essentially, this phi is known at some very fine scale over a grid, and I have subjected that to an approximation or a decomposition, where this result says you start from the finest scale and perform a decomposition, you will always end up with these set of approximation coefficients, and also my detailed coefficients at this scale would be all zeros, because the phi is orthonormal to the wavelet, which means the low pass filter is orthonormal to the high pass filter. Therefore, there are no high frequency coefficients at all. Now, I do not know what is that phi of t, but I know for sure that any phi of t associated with the low pass filter will produce this approximation and detailed coefficients at level 0. Now, I reconstruct. So, I would like to go from V0 to V minus 1. So, this here is the projection of phi of t onto A naught. I am going to now reconstruct A minus 1. I can do that, I have the reconstruction algorithm, right. So, I am going to run A naught through the reconstruction algorithm repeatedly as many times as I want to get my phi of t. That is the basic idea behind the cascade algorithm. It is a very simple one, but uses the orthonormality property. So, what you do is you choose the associated low pass filter, for whatever family you want to construct the scaling function. Just start the low pass filter, because it is all about constructing phi of t from the low pass filter, and then get your initialize your guess for the not guess, initialize your approximation coefficients at level 0. Does not have to be level 0, but just for discussion sake we say it is level 0, and then set all the details to 0 and apply the reconstruction algorithm repeatedly. And how do you do that? Well, there is a command called up COEF in wavelet toolbox of MATLAB, which will allow you to reconstruct repeatedly either the from the approximation coefficients or the detail coefficients, and then you will be able to reconstruct it at any level. All right, that is nothing but your reconstruction algorithm with all the other band coefficients set to 0. That is all. There is nothing very great about it. In fact, this algorithm now can be applied to the wavelet also, right. For the wavelet, what happens is the property of the wavelet is such that the detail coefficients, if you were to feed not the scaling function as a signal, but if you were to feed the wavelet as a signal, what kind of approximation and detail coefficients would you get? You would get the reverse situation. So, I start from psi of t, that is what I would feed, and then perform the decomposition many times. Then when I come to a very coarse scale, what I would have is all 0 approximation coefficients, because the wavelet has nothing in the low frequency band, and the detail coefficients would be 1 at lag 0, that is at time 0, and 0 elsewhere because of the orthonormality property of the psi, and that is it. So, I can also apply this to generate my wavelet, and this is exactly the algorithm that is implemented in the Wavefun. Okay. So, remember we used this Wavefun long ago in the CWT lecture 7.2 when we talked about scale to frequency. We started with a specification of the low pass and high pass filters for the Dobeschi, and then we said we specify the number of iterations to generate the scaling function and the wavelet, and that is exactly what the Wavefun does. So, let me do that 5 dB. So, if you can see here I am going through 12 or even 9 iteration, does not matter, and that gets me the dB2. In fact, if you open up Wavefun, you will see that it is exactly implementing the algorithm that we just discussed. If you throw away all of this, what it does is here here it gets the filter coefficients, and the up COEF is the key. To generate the scaling function, it uses approximation coefficients, and what are the approximation coefficients? If you go up, you will see, in fact here itself it says the approximation coefficient is simply a single coefficient of value 1. That is, you have started from phi of t and you have decomposed it to such a level that only a single coefficient is available, and that single coefficient value is 1. Right? Given any signal, I can perform the maximum decomposition such that I only have one coefficient left. And if I what the previous discussion tells us is, if I start from the scaling function itself, that is the decomposition of scaling function itself, there will come a level at which there is a single approximation coefficient, and that is the value of 1. Likewise, if I start from the wavelet and I perform the decomposition, there I can reach a level at which there is a single detail coefficient, and that is a value 1. So, the up COEF performs this repeated reconstruction, and that is at the core of Wavefun. So, let us plot here So, as you can see, this is the scaling function now over the interval 0 to 3. As you can see, it is over 0 to 3 because that is the effective support, and the result of course looks identical, at least in shape, to what we had with the previous algorithm. And if I look at the wavelet, This is how you iteratively generate your scaling functions and wavelets starting from filters. Now, what we shall do in the next MATLAB session, the fresh MATLAB session, is I am going to show you how to compute the wavelet transforms and how one can perform signal compression and how one can perform signal estimation and all of that. Primarily it will be a MATLAB session, and I will give you a brief theory of signal estimation. The basic idea in signal estimation has already been discussed. You decompose a signal and then you apply some criterion like we did on the CWT and the short time Fourier spectrogram and so on. You apply a criterion on the coefficients at all the scales or at some scales and so on. We call this as thresholding, that is, you throw away certain coefficients or you retain and so on and then reconstruct. So, the basic idea is transform, perform some operation in the transform domain and then reconstruct. That operation in wavelet domain is nothing but thresholding. So, there are several flavors of thresholding and of this basic idea, which we will discuss in the next MATLAB session. So, it will be more practice oriented and a bit of theory on signal estimation. That would be the final lecture on this topic of discrete wavelet transforms. There are of course other applications of DWT such as discontinuity detection. I will also briefly illustrate the idea of discontinuity detection in DWT and how choosing wavelets with higher vanishing moments makes a difference, different vanishing moments makes a difference in discontinuity detection. So, what we are going to do is look at how to perform decomposition and reconstruction, detect discontinuities briefly, and then spend a lot more time on signal estimation, discuss the different thresholding methods, and that with that we will conclude the topic of discrete wavelet transforms. And finally, we will have a closing session, that is a closing lecture on the for the entire course. So, hopefully you enjoyed this lecture and learned quite a bit, and see you in the next MATLAB session.